Good afternoon, and welcome to another of the CERIAS security seminars. I'm especially pleased today to introduce our guest. Simpson and I have been working together for over 20 years. It's rather amazing to me to say that. When we talk about somebody who's had an impact in the field, Simpson Garfinkel has certainly done that. He has worked as a systems developer at Next Computer Corporation. Has written a number of books, very important in the field, including the ones that I helped co-author, but several others that have had a major impact and are worth reading. He's worked as a science and technology journalist for years with a number of important stories. He started and ran an ISP. He started and ran a startup company working with security tools. Then he went back to school, got his PhD, and joined the faculty of the Naval Postgraduate School, where he's doing research in a number of areas related to digital forensics, cybersecurity, and national defense. It is with great pleasure that I introduce my friend, Simpson Garfinkel.
Well, thank you very much. It's an honor to be here. We have 50 minutes, I guess 48 minutes. This is a talk on carving network traces with bulk extractor and tcpflow. They are two tools that I've been working on. And the talk is based loosely on a talk that we gave last year. First, I want to say a little bit about Naval Postgraduate School, which is where I come from. NPS is the Navy's research university. It's based in Monterey, California, which is somewhere between Los Angeles and San Francisco. We have a military program. We have a civilian program. If you're looking for a master's degree in computer science and you don't want to pay for it, you can take a job at NPS and get a master's degree and then be guaranteed a job with the federal government when you graduate. Or if you don't get a job, you don't have to pay back your tuition. But it's not an enlisted job or active duty. It's a civilian job with the military or with any other branch of the federal government. We also have an initiative in the National Capital Region, which is where I'm based, in Arlington. We have 4 professors, some staff, some contractors. And if you're interested in writing open source computer forensic software, you should give me a call or send me email or go to my website, simpson.net, and click the contact button, because we have the ability to hire people to work on open source computer forensic software. So my research area is, my research is in 4 areas. What I'm primarily doing is end-to-end automation of computer forensics. And the problem is computer forensics is hard and getting harder. Most of the work today is aimed at making, giving analysts tools that they can drive around through the computer, and that doesn't scale. So we really need automation, and that's our first effort. We're primarily ignoring things like files. We're working instead on bulk data analysis. And the reason is there are more people coming up with new file formats, new file systems, than there are people trying to figure out how those formats work. So we just ignore them, and we try to figure out what we can from bulk data. We also have a very significant interest in applying data mining concepts to digital forensics. That's because there's been 20, 30 years of research in machine learning, human language technology, and data mining, and very little of it has been applied to computer forensics. And that's because it's hard to work with computer forensics data, and most of the people who have been working on machine learning and so forth have their hands full. So we need to bring that technology to digital forensics, and we're trying to do that. And lastly, we're working on creating a standardized forensic corpora of data that we can freely give out, and other privacy and sensitive data that we give out to qualified experimenters. And the reason is, most work that's been done to date in computer forensics has been people working with their own computers or people working with law enforcement sensitive data or classified data. And that doesn't lend itself to scientific research. So we have a large corpus, 50 terabytes of real data that is not classified, that is not law enforcement sensitive, and that is usable for doing research. And we actually use some of that data for this research here. So even though I work on stored data forensics, most of the interest these days is cybersecurity, which I loosely define as using network forensics to solve host security problems, or using network security to solve host security. So there's a lot more interest right now in network forensics than in stored data forensics. And what we find is that there's a lot of network information in physical devices that's being ignored. So there's configuration information, there's log files, there's information that you would learn in any traditional network forensics course. But what I realized a few years ago is that hard drives also have IP packets on them, real network packets that for some reason get put onto a hard drive or put in memory, and then the memory gets written to a hard drive. And there are several reasons for that. First, sometimes when attackers break into computers, they actually run packet sniffers, and those files end up on the hard drive. Another reason is that many operating systems work on packets in memory, and then those packets get written out in swap files, or they get written out as part of hibernation. And what we know is that most computer forensic tools ignore these packets. Programs like Encase and FTK don't have viewers for them. They don't look for them in unallocated space. And that's unfortunate because packets have a lot of information that might be of use for doing computer forensics. They have IP addresses, they have MAC addresses. We can learn about the people who were using a computer system. We can learn about malware that was running on the computer system by exploring the packets that are left behind. So they're like slices from the past that are properly preserved. Last summer at the DFRWS conference, Rob Beverly, me, and a student named Greg Cardwell, we presented a paper, and these are in part slides from that paper, where we showed that you could find packets doing network carving, looking through bulk data. You could find a wide range of information that was either directly from packets or was evidence of TCP connections in the computer's memory. This builds on work that was done in an open source memory analysis program called Volatility, which was done by Aaron Walters. Now the problem with Volatility is that it only does a very limited amount of carving. Our approach goes beyond what Volatility did. So it's important to realize that even though we're talking about network forensics here, we're not looking at traffic on a wire and we're not looking at logs. Instead, we are looking at disk images and at memory that might be on disk images. Now, there'd been no prior evidence whatsoever that you might find packets on disks. And in fact, when I first told Rob Beverly of this project, he thought that we wouldn't find anything because he said that the kernel separates the data from the packet header and you just aren't going to find the packets. But I was pretty sure that we would because I know that most of the kernel developers are very sloppy in their management of memory. So I figured that if the packet ever was assembled, we would probably be able to find some cases of the packets in memory. And we did. So the main contributions of this work is not just that we found the packets, but we actually came up with a methodology for writing detectors. And I'll talk about that methodology. We tested it using ground truth corpus of constructed disk images, and we used that ground truth to actually build better packet detectors. And then there's a whole bunch of engineering that I'll talk about in the middle of this talk that we didn't talk about last summer. And then we did an evaluation on a corpus of 1,800 hard drives that were bought on the secondary market around the world, and we actually found out interesting things about those hard drives. So are there any questions at this point before I go on? Yes, ma'am.
Could you please explain in more detail what carving means? Is it finding pieces of that might have been packets?
Yeah, so carving is a term of art in computer forensics, and it means recognizing data from the content of the data rather than from metadata that points at the data. So if I gave you a block of text that had an email address buried in it, your brain is very good at finding email addresses because you're trained to do that, and you would recognize that email address. And an email address carver is a tool that looks at bulk data and finds email addresses and pulls them out. So we've written a tool that looks at bulk data and finds IP packets and pulls them out. Any other questions? Now's your chance. No? Okay. So this is a Faraday cage that we have at the Naval Postgraduate School. This is where Greg Cardwell did some of his work. It's a metal-lined box. And inside it, we actually have a tactical base station for cell phones. And we have our own SIM chips. So we can take Android phones and associate them to our cell phone system and have calls to our own phones, which is really cool. And we also can do that for 802.11, and we can do that, of course, for Ethernet. So we created a series of disk images that we thought would be likely to have packets in them. And some of them were created in virtual machines, and some of them were created in desktops. And Greg Cardwell did them in cell phones, and we have those too. And the procedure that we followed was we either started with a factory fresh machine, or we started with a machine where we completely wiped it. We did a clean install. We initiated a variety of connections, and then we either suspended the machine or we had some other way to copy out either its RAM or its hard drive or both. And now we have an interesting situation because we know the IP addresses, the MAC addresses, the Bluetooth addresses of the connections that we created. And those connections are either 32-bit numbers or larger. They're unlikely to occur by chance in the disk image. So we can actually scan the disk image for those numbers. And when we find them, we have a very good chance that those numbers are from our connections. So we did that. We looked then at the context and did statistics on the context to see what is the likely n-grams that surround those numbers. And then we try to come up with explanations for why we're seeing those n-grams. What we didn't do, which is what I told Rob to do, and he disagreed with me. He did it this way, and he was right. What we didn't do is we didn't first write the heuristic. We didn't write a program that would look for IP packets. And the reasons were, first, if it worked, we wouldn't know how many times it wasn't working. We would see results, but we wouldn't know what our recall rate is. We wouldn't know if we were seeing all the packets or just a small fraction that happened to match the rules that we created. We also wouldn't know if we made changes to our rules, how likely we would be to break our recognizer. In order to do that, we'd have to look at the n-grams, so Rob decided to look at the n-grams first. So he built his disk images, and then he looked for those IP addresses in the bulk data, and these were the predecessor and the successor of 2 grams. So these are 2 bytes before or after the IP address. And the first thing that you should notice is that in one disk image, we found thousands of copies of that IP address. And there's a statistical distribution. So the majority of them were either preceded by hex 4000 or followed by hex 0016. But there were some other instances here. And then Rob, knowing a lot about network forensics and network packets, he said, well, the 4000, that's an IP flag for don't fragment. And the 0800 is an Ethernet type saying it's an IP. And the other ones are terms of service. And then the 4006, that's an IP packet with a TTL of 64. Now, TTL 64 is really interesting because it turns out that certain, actually most stacks, when they make an IP packet and transmit, the TTL is usually an even power of 2. It's usually 128 or 64. Whereas when packets are received, it's rarely an even power of 2. So using this, you can actually tell whether that's a packet going or coming in based on its TTL. You won't be right all the time, but you'll be mostly right. So using those n-grams, we could then come up with what should be the carving signature. And here it is. And there's no way for me to display the mouse up here, unfortunately. But the OX45 is the IP type 4. And then elsewhere you see the checksum is in green. And that's something that you can use to validate all the fields. But we didn't know if the checksum would always be right or not, because the checksum might have been blanked and then calculated with hardware. The light blue corresponds to discovered IP addresses. But we used this and we actually came up with a signature. Now, we also created signatures not for IP packets, But for IP sockets in memory, Microsoft Windows, when it creates a TCP connection, it creates a memory structure called a socket. And that is it's still a structure, but it's a structure that has, as you see, no green, nothing to validate it with, and fewer bytes for building that signature. So it has a port number, it has a hex 2, and then it has 8 bytes of zeros. So frequently you find 8 bytes of zeros in RAM. And as a result, the socket structure is less reliable. And we also have a structure that allows us to find Ethernet addresses. And again, the real valuable things there is there's an Ethernet address, there's a second Ethernet address, then there's a hex 0800 and a hex 45. So that's 3 bytes. So you would expect a random match on that, 1 out of 2 to the 24, 1 out of 16 million. So if you had 16 megabytes of data, you would expect only maybe 1 or 2 matches by chance. But if you have 16 gigabytes of data, you would expect thousands of matches by chance. Now, the useful thing about that is that it's a discovered Ethernet address, and you would expect that one of them would be the Ethernet address of the machine, and one of them would be the Ethernet address of the other machine on the local area network that was receiving the packet. And so you could do a histogram analysis, and the most common Ethernet addresses that are discovered are likely to be real Ethernet addresses, and then the 1s and 2s are likely to be the result of false positives. So any questions about our carving signatures? They're being presented here graphically, and you can imagine that we'd create some if statements in C code that would match bytes in array with these graphical signatures. And you could do that in any language you want. You could do that in C++, you could do it in Java, you could do it in Python, Perl. We did it in C++. So having those signatures, we now had a situation where we needed to test them. And what you would like is a program that could read the disk images or read the memory images and then run every byte of that disk image over with the signature and report on the results. And it just so happened that I have a program that does that I've been developing since 2006. And that program is called bulk extractor, and it's a tool for doing bulk data analysis. So what bulk extractor does is it starts at the beginning of the hard drive and it goes to the end of the hard drive and it looks for any data that it can recognize and it throws that data into a file. It doesn't look for file names. It doesn't try to reconstruct the files. It just tries to do the best job it possibly can do. And the reason that this is an exciting approach is that you can actually read through all the data on a terabyte hard drive in about 3 hours and 20 minutes. And traditional forensic tools that try to process a terabyte hard drive typically take 40 to 80 hours. So theoretically, we should be able to do much better. The disk doesn't seek, but it's more than just that the disk doesn't seek. It's that we're not doing this higher level analysis. We can prioritize our analysis based on the structure of the data, and if we can't figure it out, we can just throw away that page and go to something else. Now, the program itself, bulk extractor, it's written in C and C++ and GNU Flex. The regular expressions are all implemented in Flex, and that has the advantage that they all run in parallel because it's a finite state machine. It's a command line tool. It runs under Linux, Mac, and Windows. And it has a plugin architecture with multiple scanners, and each scanner can find information and report it. And some of the scanners are recursive. They can find, say, compressed data and decompress it, and then recursively reanalyze that decompressed data. So here is a structural diagram of how the program is put together. It ingests on the left hard drives, and it has a C++ iterator that extracts buffers that we call SBuffs. And then each SBuff is processed in turn by these different scanners. There's an email scanner and an account scanner, a GPS scanner. And at the bottom you see there's a hyperfile scanner that looks for compressed Microsoft Windows hibernation files. And if it finds one, it decompresses it and it drops the decompressed data up at the top. The scanners, when they find things, follows the red arrows to the feature files. When the program finishes operation a histogram processor rereads those feature files and outputs a histogram. Now, one of the problems when you take forensic data and you break it up into pages is that there's a chance that there might be data that extends from one page to another page, and then that data would be lost because you'd only be looking at the first half and then the second half. And bulk extractor gets around this problem by using what I call a margin. Every time we look at pages, we have them overlap a bit, and the overlap area is here in red. So the pages are a little bit smaller than the total amount of buffer that's being analyzed. And the way the scanners are written, if they find a feature that begins in the black area, they'll continue to analyze it into the red area. But once the byte being analyzed goes into the red area, the first byte, then the feature extractor stops and it goes on to the next page. And so this way we can deal with features that extend into the red area, but we don't pay an extra cost associated with larger margins. And the system is multi-threaded. Let's see, I think I have that coming up on the other side. So the CBUF, the SBUF, the iterator can read a variety of different disk image formats, whether it's the ENCASE01 or RAW or split RAW or MyAFF format. And it makes these C++ objects, these SBUFs. And there's a feature extraction system and a feature reporting system such that when the scanner finds something, it can just call a function to persist that into a file. Now, what's particularly nice about using bulk extractor is that it's a multi-threaded program. These scanners can be very CPU intensive. So if you have a 16-core machine, it will actually use all 16 cores at once, each core working on a different page. If you have a 32-core machine, all 32 cores will be used at once. And I've actually pinned the CPU on a machine that had 32 cores. It was very exciting. This is the only program they've ever run that has ever pinned all 32 cores. Now, a little bit of that is disappointing because that means my program is probably inefficient and we could improve the performance. But the good news is that for somebody writing a scanner, they don't have to be concerned with how to make it multi-threaded. That's all handled for the programmer by the architecture. Now, I said that it also makes a histogram. The histogram is very important. Remember the slide with the Ethernet addresses. You'll find whenever you do bulk data analysis, lots of false positives. But if you do a histogram analysis, the most common things tend not to be false positives because the false positives come from random data. So here there's an example of histograms being used to understand evidence. If we extract email addresses, the most common email address tends to be that of the primary user. And the nice thing about the bulk extractor architecture is that you can simply declare as a programmer, this feature should have a histogram automatically made. And it will simply do that for you. You can also say this feature should be processed with a regular expression, and then a histogram should be made. And we do that to pull out all the search terms from URLs. So one of the common uses of this in the law enforcement is to come up with the search terms that a suspect is using. And search terms are very probative. They tell you what a person was thinking, what they were looking for. Search terms are much more interesting to juries than the fact that information was found on a hard drive. And as I said, there are multiple feature extractors. They can be run in order, they can be turned on and off, and some of them are recursive, like the hibernation file decompression, like the PDF scanner, which will extract text and then reanalyze it. And lastly, there's this issue of the forensic path. When a feature is located, a traditional computer forensics tool will tell you the location on the hard drive. So they'll give you the address of where that email address was found or where that credit card number was found. The problem when you're pulling a feature out of compressed data is that a user will go to that sector and they'll see high entropy data. They'll see trash. And that's because it's compressed. So we can't just report the address where, or the offset where that feature is found. We also have to say how to unpack it. So in the top example here, on one of my test disk images, you go 11052168704 bytes into the image, and then that's the start of a gzip stream, and you ungzip it and go 3,437 bytes into that gzip stream, and you find an email address. This is very, very common on modern hard drives because most web servers will download web pages compressed with gzip. The web pages get compressed, they get sent down, the web browser will put them into the web cache as compressed files, and then the cache will get cleaned out at some later point. No other computer forensics tool on that's available today will find those compressed streams in unallocated area and decompress them. So for the people who are using bulk extractor in a law enforcement context, it's magic. It finds email addresses on hard drives that no other tool can find, and then it creates a histogram of those, and those histograms are typically all the other people that the target is talking to, or the web pages that the target was looking at, or the credit card numbers that the target had downloaded in a zip file. So for this project, we actually had to make 2 changes to bulk extractor, and they are now part of the release. So if you download the tool, you'll get these changes. The first is we actually had to create the hibernation file decompressor. Previously, most of the tools out there would only work with intact hibernation files. When Microsoft Windows boots, it overwrites the first few bytes of the hibernation file so that it won't accidentally be used the second time. And those first few bytes contain a table that are the starting location of every compressed page in the hibernation file and where the data goes to in physical RAM. We don't care about where it goes to in physical RAM because we're just interested in decompressing it. We look for the signature that's at the beginning of each compressed page and we decompress it. Now sometimes we have a signature, but part of that page was overwritten. So we had to take the open source reverse engineered decompressor and make it secure against invalidly formatted compressed files, which was a question of a very careful code audit. We also took Rob Beverly's algorithms and we put them into the ScanNet module. And what this allowed us to do was to run his packet carving code not on a single drive, but on thousands of drives, and not with a single core, but with dozens or hundreds of cores simultaneously. So it actually allowed us to do the experiment at scale rather than on a single machine. And the plugin architecture of bulk extractor made this very easy to do, and it gave us the high performance payoff when we did it. Now, hibernation files are really important for memory forensics because they are a copy of what was in memory. And in Windows, they're not encrypted. They are lightly compressed using this proprietary compression algorithm. And what we found was that they move around on the hard drive. And hibernation files in NTFS are just like any other file. Sometimes people delete them to get more disk space, and then the operating system recreates them. And sometimes they get moved because Windows is constantly defragmenting the hard drive in the background. Swap files also move around for the same reasons. Windows will make them bigger. Sometimes people delete them. Sometimes they get defragmented. What we found was that adding hibernation file decompression dramatically increased the number of IP packets that we found on the hard drives. And we could tell from the forensic path whether those packets were found with the compression algorithm or without the compression algorithm. And we could also correlate with another tool whether those packets were found in a real hibernation file or found in fragments of a hibernation file. And the majority of them were found in unallocated space, which probably had once been a hibernation file or once been a swap file, but no longer was. Any questions at this point? I've thrown a lot at you. Okay. So we have this problem with false positives. I've alluded to it several times. We have some techniques that we can use to minimize false positives. One is that checksum, the IP checksum. So Rob thought that, and other people thought that we wouldn't see valid IP checksums because in order to calculate the IP checksum, you have to zero that out and do the calculation and then see if it matches. but apparently the calculation functions were simply not adding those bytes in or subtracting them out. We were finding valid checksums in a majority of the packets, but not in all of them. We found it was important to eliminate bogus IP addresses like 127.0.0.0 or 240.0.0.0. We found that it was useful to do the histogram calculation. And in the paper, what we also did was we correlated IP addresses that were found in binary with dotted quads that would be found on the hard drive. So if your computer is at address 192.555 and you send out email, your mail client might embed its IP address in the mail header, and then we would find that on the hard drive. And frequently we did find correlation between the binary IP addresses and ASCII dotted quads. But we did find IP addresses in binary that were not in the ASCII. So if you really want to get all the IP addresses, you have to use this binary approach. And as I said earlier, because the 2 to the n rule on outgoing TTLs, we could actually tell whether the packet was going from a client to a server, or whether it was outbound or inbound. And then using the well-known port numbers, we could actually figure out whether our computer was running the web server or the remote computer was running the web server. And we could do that all without looking at the executables on the computer. Well, that's really interesting too, because there's a lot of peer-to-peer software for which it's interesting to know if where the server's running. So I'm going to talk a little bit about the validation. We did fresh Windows installs, and we did large file transfers, and then we hibernated the machines, and we found those IP addresses. Then we took the NIST computer forensics images, the CFREDs, and we found IP addresses, IP connections to w3.org. Usually that was to verify something having to do with, I think that was verification, but it may just be that they were downloading data from w3.org. But volatility did not find those connections. So that's another success, showing why this approach is superior to the prior work. We then took the real data corpus, which is a collection that I've been putting together. And when we did this, there were 1,800 or so images, including cameras and MP3 players. So we just ran it over the whole corpus, even like the CD-ROMs. We didn't just pull out the disks for Windows operating systems. And we found IP packets and data structures on 40% of the images. So that's interesting, but it's really a meaningless number because you don't know how many camera cards are in the corpus. You could get that information, but it tells you that it's a useful corpus for doing this kind of work. We found that the binary carving with checksum validation worked quite well on our data set. And we found that on 20% of the images with IP packets, we were able to do correlation between the ASCII numbers and the binary numbers. But on 66 of the drives, we found validated IPs that were not in the ASCII. So the message here is not the percentages, but the fact that we found it. And also it's relevant the way that we got this data. The real data corpus are computers that were purchased on the secondary market. Most of these computers were sold for a reason, like they were broken. People tried to wipe them, but sometimes before we bought them. If you were doing this in a law enforcement context, normally you'd be seizing computers that are actually in use. So our experience has been that real computers are much easier to analyze than data in the real data corpus. So this is a cross-drive analysis. The yellow blocks correspond to computers, and the blue circles correspond to MAC addresses. We took all the machines on which Ethernet packets were found, and every Ethernet packet has 2 MAC addresses, and we did the correlation. The yellow box being the drive on which it was found, and the blue boxes being what machines that blue box was talking to. And you can see that circle. Those are all computers that were purchased at the same organization. We know that from the records, but the blind correlation tells us that they were all connected to the same network. Now the little diamond in the top left, one of those computers was purchased in the Palestinian territories, and one of them was purchased in Israel. but they were both being serviced at the same computer store, and we have reason to believe that they were both put on a subnet at that same computer store and that they were talking to each other. One of these is a false correlation. That's the 5-pointed star on the right. That's actually a MAC address that's associated with Ethernet multicast. So again, one of the problems with computer forensics is that all of the details always matter. That's what makes this area especially hard to work in. Now, we presented this research a year ago. We released the software. We put Ethernet detection and carving in bulk extractor version 1.0, and nobody used it. And I was shocked. I said, there's this incredible tool. It has all these neat things. And the reason nobody used it is because all the people who were working with network forensics had tools that would only work with PCAP files. Files made with TCP dump or some other program that put packets into a file format where there was a header, and there was then a packet header which said the time that it was captured, and then the packet. Now, it's an easy file format. We just thought that our users would be more sophisticated, that they would be able to work with MAC addresses and IP addresses, but they weren't. So version 1.1, it actually finds the IP packets and it makes PCAP files. And our users have been much happier with that. Now they can use all their traditional computer forensics, network forensics tools, and analyze the files that are made from PCAPs, from packets that are found on the hard drive. Now there is a problem that if we just find a packet on the hard drive, we don't actually know why it's on the hard drive. It might be from RAM, it might be from a PCAP file that somebody had, was running a packet sniffer. So what we'll do is we'll look before that packet and see if it has a PCAP header. And we tell it's a PCAP header because the capture length and the packet length and the timestamp all meet certain sanity checks. And if so, then we put in that PCAP header, and so we now have a tool that can carve arbitrary PCAP files. And there are many organizations that have been penetrated by hackers and are running packet sniffers, and you can use this tool to find them. If the packet was not in a PCAP file, we don't have a timestamp associated with it, so we make it around 1 minute after midnight on January 1st, 1970. And that's a well-known time. It's 1, we don't use 0, we use 1 as a time t value, so they will stand out. Now, Hamming is a computer we have at NPS. It's got 2,000 cores and 2 terabytes of RAM. It's a big cluster. And I can run bulk extractor on all the disks, which are also on Hamming. And then I can just type ls-l */* PCAP, and that will show me all the disks that had packets carved off of them. When I ran this, there were only 5. There are a lot more now, but you can see that they just stand right out. And here we have disks from the United Arab Emirates, and there's a few packets. And I ran tcp dump-r, and you can actually see that those packets were from crl.verisign.net.http, which means some program was looking at the VeriSign certificate revocation list. But we actually know it was looking at the certificate revocation list, and that's really cool. And we also know that its IP address at the time was 192.168.2.129, which is private subnet, so it's completely useless. But there's stuff here that I'm not showing you, right? We also have the Ethernet MAC address. So we have the MAC address of the router or the wireless router. And if you had a list of every MAC address in your target area, we would now know which machine you were connected to. It could be in some criminal organization. It could be some peer-to-peer connection between 2 phones. This technology, in order to use it, you need that big database. So, in conclusion, and I have about 10 minutes left, which is enough time to take some questions, bulk extractor gives you a new way to do network forensics. It's the only tool out there. I know that will peg all 8 CPUs on this machine, so it's fun to look at. And the way we do this is we ignore the file system. We try to find data anywhere we can and decompress it with any approach that we can. And we've learned that you've got to produce data in a format that the users can already ingest it. You cannot get people to both adopt a new tool and adopt a new file format. That's much harder to do. So by making our data match their file format, we're able to get more people use it. So the big advantage of this tool is there's a lot of hidden data and we find it, and the multi-threading makes it really fast. And then you can use other tools like tcpflow to reassemble the TCP streams. One of the disadvantages is that we haven't temporally located the packets in those PCAP files, so it's a little screwy. You can get packets from the distant past. You can get packets from the prior user to your target. So it might be a situation where the computer was stolen and being used by a criminal organization, but you might get packets from the legitimate user. So you always have to be careful in network forensics, or in computer forensics, especially as we get these more powerful tools. We can frequently find data from people who are not the target, but who did have access to that computer. Any questions? It's got to be a question.
I'll make an observation.
Okay.
You had mentioned the w3.org address popping up, and on a lot of web pages, they have a header with a DTD file that points back to w3.org, and so that's very possibly why it's showing up a lot, is people using canned editors to create web pages that put that in automatically.
Right, but we found the IP address that corresponded to w3.org, not the host name. So there was a TCP connection to w3.org.
But if you're using one of those web pages, I think it would...
Oh, right. It's entirely possible that there was some tool on that NIST test disk that, for whatever reason, went to w3.org, maybe because it was in the HTML. Given the way that the NIST test disks were created, that's unlikely. It's more likely that they opened up a connection to w3.org and downloaded the HTML standard. But I don't remember how they made that disk. Other questions? Yes, in the back.
Just wonder how admissible is the evidence you extracted from this open source software in the court?
Oh, well, so that's an excellent question. And the answer is, it's as admissible as the opposing attorney lets it be. Right? So you can introduce anything you want if you're the prosecution. The primary use that I've seen of computer forensics data is to get the defendant to admit guilt and not go to court. And it's very useful for that. If you find data with bulk extractor, you can then go back with an accredited tool like Encase or FTK and you can find it again. And that is commonly done by my users. The main use that I want made of my tool is not in court, but as part of the investigation. I can produce a list of contacts. I can produce a list of hard drives that are thought to be part of the criminal conspiracy. And we can use that for search warrants. We can use that for questioning. A very effective use of this tool in an actual case was they showed the search terms and they showed the large collection of credit card numbers to the judge, and the judge denied bail for the defendant. They said that this quick tool had showed that there was suspicion that this really was the defendant's computer, that the defendant had intent, and that the defendant posed a flight risk. So there's many, many uses of the tool other than creating evidence that is shown to the jury. Other questions? Oh, and lastly, the fact that it's open source is actually better because that allows the other side to get a hold of it. And there are many situations where the defense actually can't use the tool that the prosecution has used. Yes, sir?
I have a question about VMs and
Sure.
how does bulk
Virtual
extractor
machines.
work when
Works
when
great.
you have compressed files inside the VM?
So every virtual machine has a different way that it stores disks. But none of them that I'm aware of compress their disk images. They use indexing and they do copy on write and so forth. So we'll just see those pages and we'll just process them out of order. Now, if you're worried about features that might cross a page boundary, you can always have your virtual machine take that indexed file and turn it into a flat file. If the virtual machine actually did compress, Almost certainly it would use zlib because that's the compression algorithm that everybody uses. And we find zlib compressed streams and we decompress them. So it would just be recursively analyzed. In fact, if you have a whole collection of files and you want to analyze them with bulk extractor, the easiest thing to do is to put them into a zip archive and have bulk extractor analyze the zip archive. And it will handle that for you. Next question. So any other questions about the packet carving? We got 4 minutes and 51 seconds left. So, well, I would encourage you all to take a look at the website. If you just type bulk extractor into Google, you'll find it. You can download a precompiled version for Windows. You can download open source for Mac and Linux. Compile it, give it a try. Burn up your CPU. And see what you can find. So it's a really good tool for doing privacy auditing. It's surprising how much information is out there. It's a good tool for looking at the results of attempts to sanitize computers. And that's, in fact, what it was originally developed for back in 6-7 years ago. So again, thank you very much.
Thank you.